I am so excited because as you guys know, maybe you guys have, joined his session before. Today we have one of our top expert engineers from the MIDAS Expert Network, which is Mr. Amir Botros. So Amir Botros is the senior structural and also bridge engineer at Stantec. He is really experienced. He has more than 12 years of academic and professional experience in civil engineering, with a particular emphasis on concrete structures and bridges. And as you can see on his bio, he is skilled in finite element analysis, computer-aided design, and also earthquake engineering. And he has a PhD focused on structural engineering from North Carolina State University. And right now, Amir is already here with us. Hi, Amir, can you hear me?
Hi, Tito. Yeah, I can hear you.
Okay, awesome. So yeah, guys, Amir is already here with us. So right now I'm gonna give Amir a chance to introduce himself, and after that, I think we can start the session right away. See the presentations, and at the end of sessions, we will have the Q&A session. So Amir, you can introduce yourself first, and after that, we can start the session right away.
All right, Tito. Thank you for the introduction, and I'm really having pleasure to be here today in this session. And my name is Amir Botros, and I am working with Stantec now, and I have been working with him for them for a year. I have 15 years of experience in the field of bridge engineering, and I also had my PhD degree from NC State University, North Carolina State University. So I have been here for a while in United States, and I am glad to see all of you today just to talk about this interesting topic that I really enjoy myself and is of primary importance in the field of bridge engineering for all of you who are working in this field. So this session is basically about construction staged analysis in bridges. And I plan today to cover some applications for using construction staged analysis in bridges. And those applications differ in the level of complexity of the bridge. So I'm basically going to start with bridges that we see every day and are very common here in US, and then move to the ones that are really advanced, or the ones that you just can see maybe 1 or 2 times in your career life. So I usually prefer talking about models rather than using presentations. So I'm going to share my screen with everyone. And
Okay.
yeah.
Amir, I'm gonna help make you the presenter so you can share your screen. And Amir, thank you so much for being here with us. We really appreciate it. And I think today will be pretty exciting. And yep, you can share your screen right now.
All right. Okay, thank you. So you can see my screen now?
Yes, I can see your screen.
Okay. So this is the first application that I want to talk about, and it's a very simple application. So this way we can take the topic from simple models and move on to more complex models later. So this is a bridge that I call it's an everyday bridge. And it is basically a precast, pre-stressed concrete I-beam bridge. And I just want to hint or make a focus while discussing this model on the topic of construction staged analysis. So I'm not really going to go on every single definition in the model, but rather I will focus more about the construction staged analysis, how to build the stages and what are the tips or the things that we need to include to make sure that we have a correct definition for the construction staged analysis. So this bridge basically consists of 4 bulb T girders. You can see this is the cross section of the bridge. So those are bulb T78 girders, and they are 4 girders spaced at 12 feet, and you have the concrete deck on top of that. So of course, any finite element model have those steps. Those are the basic steps that you need to define for any model, including the materials for the model and the section definitions. So, of course, for this span for the deck, we have a 4,000 psi concrete material. So we basically define this material here, and including the modulus, the Poisson ratio, and the weight, and the density. And for the pre-stressed girders, we will have, of course, a higher grade concrete material for the pre-stressing effect. So we have 8,500 psi for this material. And I do have a definition here for the pre-stressing strands that we are using in the bulk T section. So that's just the grade for the pre-stressing material or the steel material used for the pre-stressing. And finally, I have a definition for that I call dummy concrete. So dummy concrete is no more than a concrete definition that has a weight density equal to 0. And the reason why I'm defining this, I'm going to show later on in the model that the purpose of defining this material, that this can be set to any elements in the model, that you just want to include the stiffness of the element without including the weight of the element. I'm going to describe this more as we move to the construction stages. For the section definition, of course, we have a bulk T78 section, so we'll go and define the section definition for the bulk T78. And that is an interesting thing inside MIDAS when you open the section library, as we have really an extensive library that has all different types of sections here included. So going from all the generic sections, including the steel sections and the rectangular and circular configurations and all types of sections, going to the steel encased sections as well, like the steel sections that are encased inside concrete. And we have all different configurations here for the I-beam encased sections, encased in rectangular section or circular concrete section. And also the concrete filled steel tubes, which is also a very popular section that can be used sometimes for piles and other elements in the bridge. Then going to the combined sections, when you have two steel members combined together like this. And the one that we really use most is the pre-stressed concrete section definition. This module here is basically specific for defining the box sections for bridges, including any number of cells. And this module also can be used to define the I sections or the T sections, which are the I-shaped pre-cast pre-stressed girders. Or you can even use it to define any generic section. So this value here means that you can input the properties of the section here right away for whatever section you are defining. This is not really covered by a particular geometry that's embedded inside the software. For the I-beam, the bulk T78, we usually use the I-beam section, which is this one. And we normally have here a figure that is like a guide figure that has all the definitions or the dimension named here, and all what you need to do is to input all the numbers here for the dimensions, the basic dimensions of the section, and that's how it is defined inside MIDAS. Second thing, when of course, we know that those precast I sections are going later on, we are going to pour the deck on top of them or the concrete, and the two pieces becomes composite together. So for defining a composite section, we do have here composite section definition. So this comes when you go to add a section and you go to this tab here that has the composite section definition, and you have different shapes, including steel tubs or the I-beam sections. So I would say for the concrete bulk T section, we can use this one here and define the properties for the slab, which are the basic dimensions of the slab and the haunch thickness. And then later on for the I section, you can simply import the bulk T section that you defined earlier for the girder by itself, or the girder section by itself. You can import it from here, and that's how you end up having the definition for the composite section for the inner girder. One important aspect here is to include this ratio here. That's the ratio of the moduli for the concrete and the steel. I'm sorry, for the two concrete materials, for the concrete of the deck and the concrete of the girder. And the ratio, the reason why this ratio also needs to be included, because when MIDAS calculates automatically the properties for the section, for the composite section, we have to make sure that we include the modular ratio in the calculation, because those are two different materials that have different properties. To make sure that we get the correct stiffness and the correct inertia, we want to make sure to include this ratio in here. So this definition can be used whenever you have a composite section that is symmetric, like the case for the inner girder or the interior girder for this bridge. You see the deck here is symmetric at the center line of the girder. But whenever we get to a case like the exterior girder, when you have the overhang length is different from have the spacing of the bridge, you end up with a situation like this, that you have an unsymmetric section. This one also can be defined inside MIDAS, but this can be defined as a composite general section. So this option here provide you the capability that you can define any section that have unsymmetric geometry, like this one here. And this can be done also using or in junction with the section property calculator tool inside MIDAS. So because I actually received many requests about this definition here, I just intended to go over it here quickly with you guys. So I think I had one here. Yes. So just to go quickly over how to use this section property calculator and have a section defined with an irregular dimensions, or I would say that one that's not symmetric, like an unsymmetric section. So let's say that we have a MIDAS model here, and we already, first step is of course to define the materials inside the model, and then you will need to go to an AutoCAD file or something and draw your section with the geometry that you have, the irregular geometry or the unsymmetric geometry that you have. So here I drew the girder and the deck together in AutoCAD and save this as a DXF file. And the important thing here, when you draw the section, to make sure what units are you using to draw the section. So for example, here I used inches everywhere to draw the girder and the deck together. And then what you need to do is to make sure that you set the units here correctly to the same units of the drawing, and then you go to tools. This is the property, section property calculator, the brilliant tool inside MIDAS that you can use to create any geometry that you need. Just set the units to the correct units, including kip and inch, and hit OK. The other important step is to define the materials correctly here, because this plays a role in calculating the properties and the stiffness for the section later on. So we define the deck concrete material. I'm just plugging numbers as an example. So we have a material for the deck, and we have the other material for the girder, pre-stressed girder. Just including the modulus, the Poisson ratio, and the weight. So we have to define the two materials that we are using, and then you can simply come and say import the AutoCAD DXF file and pick your DXF file from here and hit OK. So this way you have imported the section inside MIDAS, and then you can generate, because this is going to be a composite section, so you need to go to this tool, generate composite, and let's name this exterior girder. And this consists of two parts, because now we have part number one, which is the pre-stressed girder, the precast girder, and part number two will be the deck on top. And the base material for the section will be the girder material, because that's the dominant material of the section here. And then basically you hit apply. So this tells you that this section has been generated, and then add to composite. That's the exterior section. So part number one will be the girder, pre-stressed girder. all what you need to do is to pick the shape for the girder here and make sure that you are selecting the correct lines, and then pick the material for the girder, which is the pre-stressed one, and then hit apply. And then you go to part number 2, definition, which is the deck definition, and of course name it deck. Then you pick the deck and choose the correct material, and you can even choose a different color. So this way, yeah, I think I just made a mistake in my selection, just to make sure that we do not include wrong lines. We want to make sure that we just include the correct lines in the selection, and then hit apply. So this way, the MIDAS understood that this portion will be the deck portion of the section. And then what we need to do is to go, if you hit on property, calculate composite property, and then you put the mesh size. So basically what MIDAS does, or this section property calculator does, is that it discretizes the section into small elements that are 1 inch by 1 inch in size, and it calculates the property for every single part by itself and the property of the composite section as a whole. So this way, if you go and display the properties for the section, you will see this is the girder property. So this is the yellow portion of the section, or the yellow part that represents the girder. The area, the inertia, all different properties are calculated here. And that's the deck properties, which represent the concrete slab on top. And that's the girder and the deck together. So this is the composite section properties. So this is the way how you define sections that have irregular geometries inside MIDAS. And the last step will be how to export this composite section. So you need to hit on export section, and then you select the entire section here, and you have to name the file exterior, let's say exterior 1 or something, in this extension .sec, because that's the extension that's going to be saved inside MIDAS. And after you do that, you can also save this section in SPC, the section property calculator extension, and that's how you save it inside MIDAS. Then later on, when you get to define your section here, it is very simple that you go define your composite section. Just hit on composite here and basically name your section. Choose the correct type, which will be the generic one, because now we are defining a general section that has an irregular geometry. Call it whatever, any name that you need to call, and then you import your SEC file, and that's basically the file that is saved in it. And this way you end up with the section defined inside MIDAS. So now MIDAS read the section property calculator file into this file, imported it, and imported it with all the properties. And just make sure that you are keeping the units with the correct units while you do this import process. So you make sure that you import the property with the correct dimensions and the correct properties, section properties as well. And then this way you can have your section defined inside MIDAS. So that's a way that you can define irregular sections. I just wanted to highlight this because I received some requests from people going over this definition together. So that was the way that I defined those exterior girder sections for the model, the irregular ones, this way. And of course, we will have the definitions for the internal diaphragm and the exterior. So just need to make everything active. Make sure we activate all the model. So this is the interior diaphragm. It's just a rectangular section here, and the exterior diaphragms, which are the external ones. And after we covered this part, so we defined all the sections inside MIDAS. Of course, we can go and start defining the geometry of the model. And the geometry of the model, you have here those tools to basically draw and create nodes with coordinates. Just if you hit on this, and you can create all the nodes that you need using the coordinates, and basically create the elements by simply drawing the element joining from one node to the other. So this is one way. And of course, when you create the element, you can pick the material and the section right away here to define your materials and sections for all the elements. So that is a useful way to do it. Or of course, MIDAS also provide the option that you can import the DXF AutoCAD file. So you can draw the geometry for the span, including the main girders, the cross elements, the deck elements, the diaphragms, all different elements inside AutoCAD, and just import this AutoCAD file inside MIDAS. To this way it can save you considerable time when you are building the geometry of the model, especially if this model is having curved geometries or an irregular bridge model. Then definitely defining all the loads, you need to define all your loads, including here I have 4 load cases defined for this basic span here. So the self weight is basically defining all the components of the model that have a section and have a material definition. Automatically the self weight will be calculated by MIDAS based on the material and the section definition added. And we have a definition here for what I call the deck weight, and this is basically the weight for the fresh concrete of the deck. So when we construct this types of spans, the precast, pre-stressed concrete spans, we erect the girders first on the piers. So we have a stage when we have the girders erected on the piers, and then we pour or we build the formwork between the girders, and then we cast the concrete or pour the concrete. So there is a stage where you have the weight of the fresh concrete only applied on the basic girder section, on the pre-stressed girder section. So that is not applied on the composite section, that is applied only on the girder section. So to do this, I had a definition here for the weight of the fresh concrete. I calculated using the tributary area, the share of each girder, how much the girder will carry from the concrete, the weight of the fresh concrete, and applied this as uniform distributed load on top of the girder. Also, MIDAS has the option that you can define the load eccentric from the girder if it is needed to be this way. For example, here for this particular case, you know, the exterior girders, we have the deck here is not symmetric with the girder, so we have some eccentricity that is applied here in the deck weight to count for this eccentric load. And the third load case that is created is basically for the pre-stressing effect. So defining all the tendons or the strands inside the model and adding the pre-stressing force in a separate load case. And finally, a load case added for the barriers, which is basically the 2 barriers that are applied at the edges of the bridge. And you can see here the barriers are applied eccentric from the exterior girder because that is how they are applied in the actual condition. So defining the load cases. So now this stage, you are just building the model, adding the materials in, adding the sections, building the geometry of the model, building all the load cases or defining all the load cases, and also defining the support conditions, which is really important in any finite element model to make sure that you have the correct restraints and links and everything. So for this particular case here, since I'm defining the girders, I'm putting the frames at the top of the girder, at the top of the pre-stressed girder. So I had to define some rigid links here that represent the depth of the girder, like this node lies at the top of the girder and this node lies at the bottom of the girder. So those are just rigid links connecting the frame element which is inserted at the top of the girder all the way down to those nodes which represent the support nodes. And basically we usually use elastomeric bearing or some kind of bearings that have stiffnesses, translational stiffnesses and rotational stiffness. So that's how we ended up defining here the properties for the bearing. This comes from the type and the size of the bearing and the modulus material of the bearing. That's how you can calculate the stiffness for the vertical direction for the bearing. And I choose here compression only to make sure that this bearing does not operate under tension, because those bearings can only carry compression force. And the only case that you can consider tension if you have your bearing anchored to the vent, which is not, of course, a common case or is done only in very specific cases. Also making sure to define the boundary conditions, including the horizontal stiffnesses for the bearings, like in the two translational directions, X and Y, and any rotational stiffness that you are interested to add. You can also add this in the boundary condition here. Then, of course, you will define your moving load case. And of course, the moving load case or the live load case is usually a post-construction stage, which means that this load, of course, needs to be applied after the full bridge is constructed and open to traffic. So this is not really part of the construction staged analysis, but of course, any model that you build, you will have to add the moving load case to see the live load effect. So moving to the construction stages, and that's the focus of this session today, how to define the construction stages. So to define the construction stages, you have to think about the stages that the bridge is going through while it's constructed. So here, I defined 5 cases that take the bridge all the way from the girder stage, when we have the girders erected on the bends or the pier caps. So for example, this first stage here, I'm calling it bulb T78 only, which is the girders only applied at this stage. Then I have stage that I add the pre-stressing effect or the pre-stressing force to the girders. Then I have a stage when we start pouring the concrete for the deck and the diaphragms. So I call this stage deck weight. And keep in mind, this is the weight of the fresh concrete applied on the girder only, on the pre-stressed girder only. But up to this stage, the composite action has not been generated yet. Like the section is not composite, doesn't have the two components working together, the deck and the girder. It's just the girder applied only at this stage. Then you have the composite stage. This is where the stiffness of the deck comes into play, and the section is working or performing as a composite section. And finally, you can have the barrier load or the wearing course or any type of load that comes after that is installed on top of the girder. So this is how the construction stage window look like. And basically what you do is you name the stage here at the very beginning, and there are 3 basic components in defining the construction stage. First of all, what element is going to be active in this stage? And what I mean by element can be structural element like a beam or a member in the bridge, a pier, a beam, a cross element, a deck element. And second thing, so that's the element. It opens for you a list here that includes all the elements that are defined inside the bridge, and you pick what element needs to be activated in this stage or what element needs to be deactivated in this stage. Then you have the option to move to the boundary condition, and then you pick what boundary conditions are going to be activated in this stage and what ones will not be activated. And finally, the load. So what loads are going to be included in this stage or deactivated in this stage. And to do this, MIDAS requires you to define, after defining all your model, building the geometry and including all definitions for material sections and load cases, you need to define what we call as structural groups, because construction staged analysis deals with construction with groups only, like the structural groups for all the elements in the model. So you'll see here I defined a group, I called it main girders. This includes the 4 bulb T girders, or the main girders of the bridge. I have another group that I call cross deck elements, which are basically the deck elements defined here. And I have a group for the interior diaphragm. I have a group that includes the exterior diaphragm, and just one group that includes all the transverse elements, which are the interior diaphragm and the deck elements along with the exterior diaphragms. And similarly, you will have groups defined for the boundary conditions. So all those rigid links that I'm showing here are defined in one group that I call it rigid links, and all the support definitions for the bearings, including the vertical and horizontal stiffnesses, are included in those groups here. And finally, for the loads, you will have also a group that you put the self-weight, all the self-weight of the elements in this group. So anything that MIDAS is going to compute the self-weight for based on the material and the section will be included in this load group definition. We have a load group definition for the pre-stressing effect. So all the tendons or the strands are as a load, as a pre-stressing load, are defined in this group. And we have a group for the deck weight. So the deck weight is basically this uniformly distributed load that I defined for the fresh concrete, the weight of the fresh concrete applied on the girders, and the barrier load is also included in a separate group. And the reason why we have to have this group definition completed before moving to the construction stages is that when you come and define the stages here and you add any construction stage, you name the stage here, and MIDAS reads only groups here. So to define what elements will be active, you have to select the correct group that will be active and activated here. And the same thing applies for the boundary condition, and the same thing applies for the load definition. So before running this model to look at the results, there is one more thing that needs to be defined, because this model is a grillage model. I call it a grillage model because we are using basically beam elements for defining everything, including the girders, the cross elements of the deck, and the diaphragms. So this is called a grillage model. And remember, when we defined the sections for the girders, we had the interior girder section, which was a composite section. This definition here is important for grillage models. And this definition is basically specifying in each section. We know that those composite sections are consisting of two parts. Part number one, which is the precast, pre-stressed girder. Part number two, which is the concrete deck on top of it. So you need to identify which part needs to be activated in which stage. So this way, MIDAS understands that for example, the first stage, we only have part number one. We only have the girder active in this stage. So that's why you'll see here, I wrote part number one. This is having the material for the 8500 PSI, and this is active in stage number one, which is the bulk T78 girders. Then when we get to part number two, which is the concrete deck, this has a dummy material, and that's where I use the dummy concrete material to make sure that when this part is active inside the model, it's not going to calculate the weight for this part. It's just going to include the stiffness of part number two, but not the weight. And the reason for that, because we said that the weight for the fresh concrete or the deck is applied directly on the girders, but should not be applied on the composite section. So to make this differentiation, we want to make sure that this load is applied only on part number one. And part number two, when it's applied, it's only the stiffness of the deck is operating, not the weight. We just need to make sure that the stiffness is what's included in the definition. So this type of definition here is very important to do before you run the analysis, to make sure that MIDAS understands which part is working in what stage. Then later on, we run the analysis. Yeah, this should be actually faster, but that's okay. So that includes all the analysis for the construction stages and the moving load analysis that's after, or the post-construction stages analysis. And one good check that you can do to make sure that you define the construction stages correctly, and that the correct parts are included in the appropriate stages of the analysis, is to display. I'm just waiting on this to finish and we'll show you. Okay, so the good thing that you can do also to check that you define the correct parts is going over the construction stages. So if we pick the first one, make sure that you only see the elements that should be active in this stage. So this stage, for example, part T78, we should include the girders. And basically, it's only part number 1 of the girder, which is the pre-stressed girder. And we should see also the elastic links or the rigid links that we have and the nodes for the bearing. So if we display the nodes here, make sure that you see those elements only active in this stage. And if you want to see an extruded view, you can just activate this option here that shows you an extruded view. So you can see clearly this stage only consists of the application or the erection of the pre-stressed girders on the supports or on the bearings. And then you go to stage number 2, the pre-stressing effect. This is only going to show that the strands are active at this stage, or the pre-stressing effect is active at this stage. Then you go later to the deck weight. The deck weight is only including the load, only the weight of the fresh concrete applied as a distributed load on the girders. So there are no elements that are active in this stage. It's just the weight of the fresh concrete applied on the non-composite section or the pre-stressed girder section. Then when you go to composite girder, this stage is the stage where you see the transverse elements or the cross elements of the deck active, and that's why you can see now the deck is showing up, and also the end diaphragms and the interior diaphragm, all those elements are being activated at this stage. And the thing that I mentioned earlier about how to make sure that the deck, when the deck is active, it's just activated as stiffness and not activated as weight, is this definition here. When you define the components of the section and you define that part number 2, which is the deck, is going to be active at this stage, and it is taking a dummy material, so it does not include any weight, it's just the stiffness of the deck. And then finally, the barrier, it's going just to apply the weight of the barrier on top of the bridge at this stage. Of course, anything that you see post-construction stage is basically the live load effect or the moments from the live load. Now, if you want to display the results, for example, see the bending moments on the girders for the different stages, you need to select the stage by stage and, of course, show the frame element view, the bending moment, and hit apply. So, for example, this bending moment here is a moment applied on the girders at this stage. There are two options here, either to see the moments coming from dead load only. That's the effect coming from dead load. And if you hit on tendon or primary, this is going to show you the pre-stress, moment coming from the pre-stressing effect. And if you hit on summation, this is going to give you the summation or the resultant of the two moments, which is, of course, what we are interested to see. So at this stage, the summation, of course, is going to be only the dead load because the pre-stressing effect is not active at this stage yet. But when we go to the pre-stressing here, you will see now the moment shifted upwards because now the pre-stressing moment kicked in, and this summation here represents this is the final moment on the girder, including both the dead load or the weight of the girder and the pre-stressing effect. If you switch to deck weight, you will see now the pre-stressing effect is starting to reduce or decrease on the girders because now we are adding more loads or more weights. That's the weight of the deck kicked in and counteracted the effect of the pre-stressing. And then when you go to the composite girder, this is where all those elements are active now. So the composite stiffness or the composite effect is now active on the bridge. And you will see there is no moment change between this stage, the deck weight. This moment is basically the same here between the deck weight and this stage because all those elements, all those cross elements were defined in the model using a dummy material. That's why we defined this dummy material here. You see all those elements have the dummy material to make sure that when those elements are activated in that stage, we do not include any weight. We are just including the stiffness and the transverse effect or the effect of tying all the girders together in the transverse direction. But we should not include the weight of those elements, because we have a load case here where we added the weight of the deck and it is acting on the non-composite section. And finally, when you go to barrier, that is going to show you the total moment on the girder, including all the effects up to this stage, adding the barriers on the bridge. Looking at the live load, you will need to go to the post-construction stage and display the bending moment due to live load. Select whatever the case that you will be checking and the moment, and you can display. So this moment here represents the moment coming from live load only. That's not the total moment on the bridge. That's the moment coming from this case only. If you want to see a combination, you can go under results here, add the load combination with the load factors for dead loads and live loads, and display the total moment, including dead load effect and the live load together. So this model here represents a grillage representation of a precast, pre-stressed girder bridge. And there is one other model here also that I wanted to talk about. That model represents if you choose to model your bridge using deck elements or shell elements, plate elements for the deck, rather than using grillage model or beam elements for everything. So this model here consists of 3 LU girder, the U girder shape, which is really very popular as a pre-stressed girder. And basically the plate elements here are included to represent the deck. And I'm just going to go directly to the definition of the plate girder. It's very simple, just defining all the plate girders in the deck and defining all the load cases, very similar to what we had in the grillage model. The basic difference between the plate element and the grillage element is how the load in the transverse direction is being distributed between the girders. So grillage models are generally known to be more rigid than the deck elements because those do not count for the flexibility of the deck in the transverse direction in distributing the load between the girders. So that's why people prefer to use plate elements to be more realistic and simulate the behavior better and the live load distribution in the transverse direction. Using these models with the plate elements, you still have everything defined, but the difference, the basic difference between this model and the grillage element is it saves you some time from defining the composite section for construction stage. This definition that we showed before, we have part 1 and part 2. For the section, this is no longer here because basically we have defined the girder here using a grillage model or a beam element to define the girder, and the deck is basically defined using a plate element or a shell element. So those are 2 different elements in nature. So this is not one beam element or composite section. And the important thing here, I'm just going to run the model to show a basic thing that we need to pay attention to while using the plate element models. Okay, so now it's close to finishing the analysis. And now you see the definition here for the stages of construction, similar to the previous model. We just have a stage that we only have the U-girders activated in it, and of course the support conditions need to be activated. Those elements, by the way, are just defined here using beam elements, so you can see clearly I'm using beam element for the U-girder or the U-beam definition. Then after that, you have a stage for the pre-stressing effect. So I'm just defining here the strands or the pre-stressing strands for the girders. Then a stage for the deck weight. This is after pouring the deck on top of the girders. So this is just adding the uniform distributed load that is applied on the non-composite section. There are no elements that are active in this stage. It's just the load of the deck. Then the composite girder stage, which is basically the stage where we activate all those deck elements to represent that the deck now is being poured and hardened, and now we have the composite section active. So we have the stiffness of the deck added to the girder, and now we have the composite section performing at this stage. So that's the compression, the composite girder stage. And also another tip, it's very important when you define the plate elements here to use a dummy material. Make sure that you don't have weight for the concrete for those plate elements. So when they are active at this stage, you just activate the stiffness, but not the weight, since the weight is already applied as a uniform distributed load that is applied directly on the girders. Then going to the following stage, which will be the barrier load. So this is just adding the barrier load to the span, and finally the wearing surface or the wearing course. One of the important aspects when you use the plate elements inside the models is to show, when we display the beam, the bending moments on the girder or the beam. Let's say first stage here where we have the U-beam only active in the model. We'll just show the frame element. So that's the bending moment for the girders only. The girders only active at this stage. Then the pre-stressing effect. So you want to make sure that you are displaying the summation here for both the pre-stressing and the dead load effect of the girder. And then moving to the deck weight. So you will now see that the pre-stressing effect is even the moment coming from pre-stressing. I'm sorry, just display this. Okay. So now you see from this stage where we have the pre-stressing and the self-weight of the girders applied, then moving to the deck weight after pouring the deck. So now the moment reduced on the girders because the pre-stressing effect is now reducing due to adding more loads or adding more weights on the girders. So the deck weight kicks in, and then the composite stage when we added all the plate elements to the model to indicate that now the deck is hardened and we have the composite section in operation, and we have all those deck elements tying all the girders in the transverse direction. Then adding the barrier and adding the wearing course or the wearing surface. So that's how you display the bending moments to see the moments on the girders at each construction stage. The most important thing when you display the live load effect is basically showing when you see the moments on the girders, you want to make sure that you are seeing the moment on the composite section, not on the frame element or the beam element of the girder itself. So this option here, when you see beam diagrams, this shows you the bending moment on the beam. But the live load effect is now acting on the composite section. So to make this, or to make sure that we are seeing the correct moment, we need to define groups here where we define the beam elements for the girder and the plate elements that are surrounding it in one group. So I'm calling this one girder number 1, girder number 2, girder number 3. So I have the beam elements and the plate elements defined in one group. And then MIDAS provides us with an option here called resultant force diagram. So resultant force diagram shows you the bending moment on the composite section. So the plate element and the beam element included together, and you can pick whatever load case for the live load that you are interested in, hit apply, and you will see the bending moments. So those bending moments are the moments acting on the composite section that includes the girder section and the deck together. You see this moment here is 5,000 kip feet. However, if you go and display the moment from the beam diagram under this live load case, you will see the moment is completely different number. That's only 2,380 kip feet. The other one was 5,000 kip feet. So it's very important to make sure that you are seeing the correct moment and displaying the moment on the composite section, not on the beam section. All right, so now T2, I see now this is 3 p.m. So I had in mind to present two complex models, one for a 4-span continuous steel girder, and going over one of the segmental models, like the ones with the balanced cantilever. So I just want to make sure, do we have enough time for that, or you prefer to take questions?
Amir, I think if you are okay with the time, you can like present the models right now. And I think for all the attendees, if you guys can like stay, you can stay. But if you guys like want to leave right now, that's also okay, because eventually we will record the session and we will put it on our website, Amir. So I think you can go on with the models.
All right. Okay. Thank you.
Thank you.
All right, so the next model, this one is having a little bit of complexity because, and this model is really a very good example of how to use construction staged analysis in bridges that are, I would say, relatively more complex than the precast pre-tensioned ones or the precast pre-stressed ones. So this example here represents a 4 continuous span steel plate girder bridge. And this bridge was a job that I worked on. Actually, this bridge is crossing over I-10, so it's crossing over an interstate. And the bridge got hit by a freight truck. So one of the trucks that's passing under the bridge here, it hit one of the plate girders that is carrying the bridge. And the damage was very extensive to the point that only the feasible solution for this problem was to replace the damaged portion of the girder. So they needed to replace some portion of the girder here that was hit by the truck. And of course, analyzing something like this is just by hand or doing calculations is not really easy. You have to go and build a full finite element model for the bridge because of different aspects of complexity in this bridge. So the first piece of complexity is that this is actually a curved bridge. So the geometry is adding one piece to the complexity. The second thing is that this is 4-span continuous steel plate girders. So the continuity also is another challenge. It's a statically indeterminate bridge. And the third piece is now you are going to take a portion of the damaged girder, take it out, and add or replace a new girder in. So this means that you are changing the statical system of the bridge. So instead of having a 4-span continuous plate girder here, you will come at some point and take part of the girder out. So you are transferring this 4-span continuous girder to 2 portions or 2 discontinuous girders with cantilevers. So this is basically changing the statical system of the bridge. And add to this that this bridge was really built in old days, and the girder or the plate girders were not composite. So those girders do not have shear studs connecting the deck to the beams or anything. So just to give you an idea about this, the cross section or for that bridge, that's how the bridge look like. Bridge consists of 2 plate girders, so that's not a redundant system. It's only consisting of 2 primary elements or main supporting elements for the bridge. So it becomes more critical when dealing with a bridge that doesn't have elements of redundancy. And the system of that bridge is basically consisting of the girders, the main girders. So I can show the groups here. So those are basically 2 plate girders that are running parallel to each other, and they are curved. Those are the continuous ones. And we have a system of floor beams that is tying those plate girders as well. Okay. So we have floor beams in this direction that are tying those two plate girders together, and we have the deck elements that are casted, or the deck is poured on top of that. So the deck is supported on floor beams, and the floor beams are transferring the load to the plate girders, and the plate girders are transferring the load later on to the hammerheads where they are supported. Also, one aspect about this bridge is that the condition between the substructure and the superstructure is different at every particular pier. Like, for example, here, the two plate girders are supported on bearings on the hammerhead. Here and here at those two supports. Here, the bridge at the end is supported on an abutment, so they are supported on bearings on the abutment. Those two supports or substructures here are monolithically attached to the superstructure. So here we have the plate girders are framing into the cross girder or the cap of those two substructures here. So all those different features or unique features about this bridge make it more complex to analyze and to investigate how to build the construction staged analysis for repairing this bridge. I would say this is just repairing the bridge. So to do that, first of all, of course, you will have to start by defining all the materials. Like, imagine yourself that you are building the bridge in the final stage, in the service stage. All the elements of the bridge included in the model, including the plate girders, the floor beams, the deck elements, even the substructures, like including the hammerheads, the columns, the caps, everything, and include all materials, the boundary conditions, the load cases for the bridge, including the self-weight, the barrier, all different types of loads are defined. So as if you are defining the bridge on the final stage in full. And then I started here defining the construction stages for the repair. How are we going to do the repair for the bridge? So starting here from a stage, I call it service dead load. So this is basically the bridge operating under the dead loads, because now we are repairing the bridge. So we close the bridge. The bridge is not allowed to have any traffic on top of it. So we don't have live load. It's only the dead loads of all the members of the bridge. So that's why I call this case service dead load. And if you see, this is defined to include all the groups of the bridge, including the substructures, including the floor beams and the plate girders. All the elements are active at this stage. And of course, the boundary conditions, we have to make sure that we are including all the boundary conditions at this stage, and also the loads, including the self-weight and the barrier, because those are the only loads applied on the bridge under dead loads. So this is the first stage that is defined. Then,
okay. Amir,
yes.
can you hear me right now? Amir, I think this part is really like it's really interesting, and I was thinking maybe we should do like another workshop session for this part, because I believe all the attendees want to like learn about this section in like separate session, so that way you can be like more focused and dig deeper in this like section. Do you think it will be feasible to do it?
Yeah, of course, I don't have a problem, definitely. This model is really very interesting, like you said,
Yeah,
and
so I agree with you. But yeah,
features that you don't see every day about span removal and girder removal. So I just didn't want to start with a model like this before giving some background about the basic and simple models first. To introduce the topic of the construction staged analysis on simple analysis first, then before jumping to more complex models.
Yep, I see. I agree with you. And that's why, yeah, I think this will be really exciting for us. And I think we should do like, separate session for this. So that way you can like, explain about it, like, into like a deeper explanations, and the audience can also like, focus on this like, interesting case. So I think right now we can move on to the Q&A first. So you can like answer like some questions, and for this part I am so excited. I think we need to do like separate sessions. What do you think?
Yeah, sure.
Okay, that sounds good, Amir. And guys, I will give you 1 minute to put in the questions into the questions bar right now. And while we are waiting for the questions, I have a favor. Basically, I need you guys to answer this quick poll. while we are waiting for the questions, I will give you guys like 1 minute and then we can start on the Q&A session. Yep. Right now, on the screen, you guys can see the one question about our content and service, because we always want to improve and always want to try to give you like the best experience with our content and services, like webinar, workshop, article, website, and social media content. So it will be really amazing if you guys can give us like your answer about this question, just like one question. And after this, we can move on to the question and answer session. So guys, don't forget to put the questions on the question bar, because after this, Amir will discuss about the question right away. And I think, Amir, right now, a lot of people asking about, can you share some of the model beforehand?
Yeah, I don't mind, of course, no
Okay,
problem.
I think guys, Amir can share it to me after the session, and when we post the session on our website, I will post the model on our website. I think that will be the best way for us. Okay, I think a lot of people has put in the questions on the question bar, and also a lot of people also think that the model is really interesting and further session will be greatly appreciated. Yes, Amir, I think a lot of like all the attendees agree that you need to do like more session for the model.
No problem, sure, it's okay.
Okay, I think we have the question right now. I'm gonna close the poll and I'm gonna share my screen.
Yes.
Okay. Okay, guys. So Amir, I think right now we have the first 10 questions. I think you can answer like, all of the 10 questions, or if you don't have like, time, we can answer like the first 5 questions. The first one is from M. Shaifuzaman. Exterior girder section, solid deck looks different than interior girders. Could you please explain about this?
Yeah, the reason for that is basically coming from the geometry. Like the overhang length of the bridge is not equal to 1/2 of the spacing, and this situation happens most of the time. So whenever we have a situation like this means that the deck is not centered with the girder, so you end up with an unsymmetric section, and that's why you will have to have a separate definition for those unsymmetric girders.
Okay. I think that's pretty clear. The second question is for composite eye girders, how to consider effective deck with in MIDAS automatically. Per STO in the main direction, only a portion of the deck would be considered as effectively resisting the load from Xiaofu.
Yeah, I mean, for composite eye girders, how to consider effective deck widths in MIDAS automatically. I think that that is something that like when we model the bridge, we actually decide this effective depth width because we are basically modeling the girder using tributary area from center to center. That's most of the models are built this way, and I think this should be a reasonable assumption for the concrete for the effective deck width. But there is no
Okay.
other way. If you want to do it in another way, if you, for example, I would recommend you can go to a plate element model and you define the particular elements that you are interested in to be associated with the beam elements in one group and consider this your effective deck width. But this can be done in the plate element models, not the grillage models.
Okay, thank you. And next question from Andrew Dawson. Why were 3 nodes and rigid links used at each of girder ends to represent an elastomatic bearing instead of just one?
Yeah, so that's a good question. So basically, what I started with, usually you start going from point A to point B in straight line. You don't use any other way to do it. But I started using one rigid link and one node. But I discovered that when you include or introduce the rotational stiffness of the bearing, this introduces some fixity at the end of the girder. So it's partially fixed, and this can end up seeing, you can end up seeing some negative moments at the end of a simple beam or a simple supported girder. which is not, we are not accepting it from a structural standpoint. We assume that the bearing provide full rotation, and we don't expect to see any negative moments at the end of a simple span. So if you are interested to include the rotational stiffness of the bearing inside the definition of the bearing, you will need to figure out or come up with an idea to avoid having any restraint for the rotation at the end, and basically avoid having this partial fixity thing. So I came up with the idea of including 3 nodes distant away from each other. So basically representing the bearing widths on 3 points, and staying away from including a rotational stiffness for the bearing.
Okay, thank you so much. And next question from Hashim. How do you define groups?
Yeah, defining groups is very easy. So what you need to do is to define the groups by name, like for example, girder group, and or a deck element group. Just define the group with name, and then later on you go and select the elements that will go inside this group and assign them to the group. I can show this on the screen if needed, but it is just a simple way, just defining the group with names first, and then you pick the elements and assign them inside the group. It's just a graphical way of doing it.
Okay, do you want to share your screen to answer the question? Or okay, cool. I'm gonna make you the presenter right now.
Right, sure.
Yep.
So if I understand the question exactly, like what hashing means, defining a group, I'm sorry, just a second, yes. So defining the groups. So how I come up with the names of those groups, or how many groups do I need, this is basically based on how the construction stage will be configured for this bridge. Like for example, when I build the construction stages here, I know that I will have a stage where I will have the girders only active at this stage. So I have to have a group that contains the girders only. And then for the pre-stressing force effect, I will have to have a load group that includes the pre-stressing effect. For the deck weight, I will have to have a load group that considers the deck weight. For the composite elements, I will have to have a group that considers all the diaphragms and the cross elements that are modeling the deck, or the cross elements that are needed for the deck. So that is how I figure out how many groups do I need. And basically defining the group is very simple. Just you go and define the name for the group and pick all the elements that go inside this group like this, and you can just go highlight the group and assign them inside the group. So if I assign them here, now this group includes those elements. So I hope I understood the question.
Yep, I think that's really clear, Amir. Thank you so much for that. Okay, next question from Jordan. Is it possible to define different load combination for each construction stage? When I have tried this, it will only let me view results from individual construction stage load cases, but not load combinations involving construction stage loads.
So is it possible to define different load combinations for each construction stage? I think I've done some, I've had this application in one of my models before doing it. I think this is possible. I just need to dig out here and yeah.
Sorry, if you don't mind, I'll just add a few comments. For Jordan, if you had any trouble like seeing the load combinations, it's probably because your load case type is specified as non-construction stage load case type. So in order for your loads to be like properly showing and also showing combination, the load case type needs to be like CS, like when you define the load cases. But yeah, if you're using, for example, just dead load, DW, DC, like things like that, then it's not going to be recognized by the program as the construction stage load. So if you define the load case type to CS or construction stage, then you're going to be able to see them properly in the construction stage, as well as being able to see the load combination.
Okay, thank you so much, Angela. And Angela is like one of our MIDAS teams. And Amir, do you want to add more explanation to answer the question?
That's perfectly exactly the thing. Whenever you have a model that has construction stages and you include the stages inside the load combination, you need, of course, to define it under a construction stage type, not under the load type, not under a dead load type or a barrier type or a wearing course type. It has to be under construction stage.
Okay, thank you so much for the answers. Next question is, why need 3 rigid link to model a support from Francesco?
Yeah, I think this question, I just answered it before in number 3. It was the same thing.
Oh,
Just
oh
repeat.
yes, yes, I'm so sorry about that. But
It's okay.
yeah, okay, I think the answer is the same. And
Yeah.
move on to the next question from Hashim. What is base model at top left of the screen? I think he was referring to.
Yeah, base model is just the module that shows you the entire model without displaying a construction stage. Like whenever you go and pick a stage, it's going to display to you the elements and the load cases that are only included or activated at this stage. A base model means that this is all the model definitions and all the elements included in the model. Um, that's my understanding for this. And yeah,
Okay,
and yes.
and I think next question is the construction stage summation load cases is the sum of unfactored loads, correct? Is there any way to include a load combination from Jordan?
Yeah, I mean, of course, the summation load case is just adding up the load cases that are included in the construction stages altogether, like all the dead loads and the pre-stressing effect that is included. This is all unfactored loads because at this stage, I'm just defining all the loads unfactored. For including a load combination, of course, this is possible when you go under results and open the load combination window. You can define the load combinations that you need to define, and you can specify the load factors that you want to specify for each load case. So this is how you factor your load cases inside and add them up together for a load combination. And also be aware when you are dealing with a model that has construction stages that you define all the load cases that are included inside the construction stages under a construction stage type.
Okay, thank you so much. Next question from Mohammad Saifuzaman. For construction stage analysis, pre-composite section shall not be designed using this step, which is load settlement pre-composite section, correct?
A pre-composite section shall not be assigned using load settlement miscellaneous. No, I think this is something else. Like this is under settlement loads. That's something different.
Oh, I see, I
I'm
see.
not sure if I
Okay,
understood it properly, but yeah, it's not definitely. It's not under settlement miscellaneous. That's something different.
okay. Actually, Amir, we have like so many questions right now. And guys, thank you so much for the enthusiasm. But I think we can answer the 10th question as the last question today. So from Hashim, in the box model, the slab is defined between center of girders, which the span is longer than real between webs of box. Is that okay?
Yeah, I mean, like this is for sake of analysis, we are dealing in any finite element model, the idealization is always done at the center of the element, or that is something that we are used to. So we are basically defining the slab from center of girder to center of girder, assuming that the slab is spanning over the entire distance from center to center. That is like a conservative way of analyzing it because we are assuming a larger span than the real one. The real one is basically from the face of the web to the face of the web. Or if you have U-girder shape, for example, so this is completely different. Like there are ways that you can overcome something like this if you want to include the thicknesses from flanges of the precast girders or something. If you are defining a plate element model, you can thicken the plate elements that are around the flanges, that are around the webs of the eye sections to include the thickness of the flange of the girder inside the model if you need to do that. But it is okay from a point that you are conservatively doing the analysis and assuming the slab is spanning from center to center of girder.
Okay, Amir, thank you so much. And guys, I think for the rest of the questions, I will email it to Amir, and Amir can answer it. And later, I will post it on the website. And for all you guys who asked about the recording and the model, Amir will share to us, and we will post it on our blog on our website. So please make sure go to our website and also check the blog, because we will post it most likely next week on Monday. So please check it. And Amir, next slide is basically just like, a lot of people thank you for the great presentations, and I do agree with that. It was really insightful. Thank you so much, Amir, for your time. And I think all of us are agree. We are looking forward to another session to discuss about the interesting model you presented at the last session, right?
Yeah, sure. Yeah, it's a pleasure for me always to be here, and I really enjoyed very much. I enjoy this topic and using MIDAS. Thank you very much, Tito. Thank you.
Okay, Amir, we will follow up with you for the next session. And guys, please stay tuned with our invitation, because Amir will also present the models next time in our session. And for all the attendees, thank you so much for your time. Hopefully this session is insightful for all of you. And yeah, happy Friday. Have a good weekend. Thank you so much, guys. Thank
And
you,
all
Amir.
those who say thank you messages to Amir, we'll make sure to deliver them to Amir. Thank you
Yep.
all very much. And Amir, thank you so much.
You are
Yep.
welcome, Angela. Thank you.
Yeah. Thank you so much, guys. Happy Friday and have a good weekend. Bye.
Bye.